Hi everybody. This lecture today is about light emission. Let's get into it. Oh, look at this thing here. This looks like, see all these this looks like an emission spectra with some absorption lines inside. That's what we're going to do today. Okay. Reminder, electromagnetic waves. We talked about these. It's a oscillating electric and magnetic field that self-induce each other. Okay, and they're at right angles to one another. And I think in this picture, the magenta one is the electric field, and the blue one, or cyan one, is the magnetic field. So light originates from accelerated motions of electrons, and electromagnetic wave propagates outward from the vibrating charge. And we have this spectrum that goes from these long, low-energy radio waves all the way to short wavelength gamma rays and everything in between. And visible light is this small small section of the spectrum where we see. And these are our ways of characterizing a wave. There's wavelength. So the wavelength is how over what distance does it repeat. Period is over what time does it repeat. Frequency is how often does it repeat in time. Amplitude is in this picture the highest strength of the electric field or highest strength of the magnetic field. There's polarization, so we can orient the electric field and magnetic field in certain directions using a polarizer. The velocity we know depends on the medium. And, well, okay, this is mechanical versus E&M. Mechanical waves like sound need a medium. E&M can propagate through a vacuum. Okay. Now the reminders that we have the Bohr model of the atom, where there's the nucleus in the middle, and then we have an energy shell n equals 1, energy shell n equals 2, energy shell n equals 3, and there's more of them. And if an electron goes from 2 to 1, it emits a photon when it loses energy. Okay, and that photon is light. And more about Bohr model of atom and light emission. So one thing is they're discrete. Okay, so we can't go from, and if these are energy level 1, 2, and 3, we can't go from 3.25 to 1.75. We're not allowed to do that. We either have to go between 1, 2, and 3 only. So they make quantum jumps between the energy levels, and that's it. So in this case, we have 3 energy levels. We could go from 3 to 2 and emit light. We could go from 2 to 1 and emit light, or we could go 3 all the way down to 1 and emit light, and that's it. Okay. So excitation is when electrons are hit with a photon and bumped up to a new energy level. And I guess what are we going to call this? If this is n equals 1, n equals 2, n equals 3, and when the electron goes from n equals 1 to 2, it's excited. And so it gets excited and it's in an excited state. And then when it jumps back down, it releases a photon when it goes from 2 to 1. The energy of the photon is given by this formula, E equals Planck's constant times the frequency. Okay, and this process going from 2 to 1 or 3 to 1 is called de-exciting. Which has less energy per photon? Red light, green light, blue light all have the same. Well, longer wavelengths have less energy per photon because they have lower frequency. So if the energy of a photon is equal to Planck's constant times its frequency, then the lower frequency light will have lower energy per photon. Well, the lower frequency light is red. Excitation is the process in which electrons are boosted to higher energy levels in the atom. That sounds good. That's this process where the electron gets boosted. Atoms are charged with light energy. That doesn't even make any sense. Atoms are made to shake, rattle, and roll. That also doesn't make any sense, so A is the best answer. Okay, this is the different types of spectra we see. So, see this line is just continuously changing in a smooth fashion. That's a continuous spectrum. If we see a continuous spectrum with some subtractions that are jumpy, that's an absorption line spectrum. If we see a continuous spectrum with some emission lines added to it like spiky things, that's an emission emission line spectrum. So this is absorption because light was taken out of the continuous spectrum. And this is emission because energy or light was added to the spectrum. Okay, so let's think of what an emission line spectrum is. Because emission means to emit. So we have a cloud of gas emitting this light in the form of these arrows here. If it goes through the prism, then we see this. What do we see when we put it through the prism? Well, we know this prism breaks it into the different frequencies and wavelengths of light, in this case, the different colors. And instead of seeing a continuous spectrum, we see discrete colors. So a couple purples, blue, a couple of greens, yellow, and some reds. So that means the cloud of gas wasn't emitting a continuous spectrum. It was emitting at these discrete frequencies, probably because it is made up of atoms, and those atoms are getting excited and de-excited at these discrete energy levels that are allowed for that particular gas. So these would correspond to those energy levels. So a thin or low density cloud of gas emit light only at specific wavelengths that depend on its composition and temperature, producing a spectrum with bright emission lines. So absorption, if we have a continuous spectrum that's emitted from, like, say, an incandescent light bulb, and if that light goes through a cloud of gas, then those wavelengths are absorbed and subtracted from the spectrum. So instead of seeing these emission lines, we'll see absorption lines, and that will correspond from the electron getting excited and absorbing the light. A cloud of gas between us and a light bulb can absorb light of a specific wavelengths, leaving dark absorption lines in the spectrum. So we see here. Then a continuous spectrum is, don't put any gas in between. Let the incandescent light source just give a continuous spectrum. So emission spectrum. Since the pattern of energy shells is unique for each element, the set of emitted photons will also be different for each element. So that means each element has its own fingerprint of emission lines and spectral of emission and absorption lines. A spectroscope is a device to see the spectrum of light that is emitted from the atoms of an element when the electrons get de-excited to lower energy levels. So that's what we would see through a spectroscope here. And these lines here are called spectral lines, and it's a chemical fingerprint for each atom, or in this case, element, which is made up of atoms. I guess atoms are the thing, element is the position on the periodic table. So we can look at something in the sky or somewhere else, look at its emission spectra and say, oh, we know what that substance is. So chemical fingerprints, so this is the helium spectrum, the sodium spectrum, the neon spectrum. And if this is all put together, we can see the lines right here in something we're observing. So if we're looking at a distant star, we say, we see the neon line right there, or we see a helium line right there. We can see what the star's made of. Most of what we know about atoms is gained by investigating the masses of the elements. Partially true. Electric charges of the elements, also partially true. Periodic table of elements, we also get stuff from that. But D is the best answer. Incandescence, black body radiation. So this is incandescence. Since the object is composed of many different atoms, we see a continuous curve. Rather than individual spectral lines. So radiation curve of brightness versus frequency for emitted light. Different frequencies have different intensity, which depends on the number of photons emitted at that frequency. The peak frequency of radiation emitted by a hot body is proportional to the temperature of the hot body. So if you're at human temperature, 98.6, that peak is in infrared. If you're looking at a candle, the peak is going to be in like that yellow-red zone. And that frequency is proportional to temperature. Okay, so absorption spectra. So here's an absorption spectra. We have a continuous white light spectrum with some lines subtracted because of absorption. So because these Those atoms can absorb photons with those same energies. Upward transitions produce a pattern of absorption lines at the same wavelengths. Okay, so that means when the light comes in, there's a characteristic jump excitation that grabs the energy out of the light and gives these lines right here. Okay, and a spectroscope can detect dark lines and otherwise continuous spectrum. Okay. Fluorescence. So fluorescence is many materials excited by ultraviolet light emit visible light upon de-excitation. The electrons in these substances get excited when illuminated with ultraviolet light and subsequently de-excited, emitting visible light. Okay, so in this picture, here's an atom with energy shells. Ultraviolet light comes in, gets boosted from n equals 1 to say n equals 4. And then when it re-emits, it goes from 4 to 3, 3 to 2, 2 to 1. And so those are much lower energy and visible wavelength light. So it can absorb UV and then emit invisible. So here's a picture here. If, this excitation, de-excitation process is like leaping up a small staircase in a single bound, then descending 1 or 2 steps at a time, rather than leaping all the way down in a single bound. Yeah. So if the ultraviolet light goes from first step, excites the electron to the top step, and then it can de-excite in smaller steps. And these smaller steps will emit visible light, whereas a full step would have emitted ultraviolet, but it doesn't do it. It does it in small steps. An atom that absorbs a photon can then emit one only at the same energy. That's not true. We know it can emit one at the same energy, but it could do it at lower energies. Of any energy, depending on the situation, well, it's not any energy. Only at higher energy, well, that's not right. You can't put in a little bit of energy and get a lot of energy out. Only at the same or low energy. That sounds like the best answer, D. Phosphorescence. So phosphorescence, so it's the same thing, except it happens in a delay. So when excited, certain crystals, as well as some large organic molecules, remain in a state of excitation for a prolonged period of time. Okay, so we don't have to read all this, but if you can excite a material by shining ultraviolet on it, and then the de-excitation process may take a long time, and in that, while it's happening, then the material will glow. That's phosphorescence. Okay, lamps. Lamps are like an incandescent lamp. It just sends electric current through this little filament, and that brings the temperature of that filament up into the visible, brings the temperature high enough that the emission is in the visible. Whereas fluorescent lamps use a different process. Well, we're going to get to, did we talk about fluorescence? We did. So it uses this principle to emit light. And that's a fluorescent light. And these are more efficient. Which lamp is more efficient for emitting light? Incandescent, fluorescent. Okay, we just said that. Fluorescent is more efficient. So light waves in phase and out of phase. So here's white light with many frequencies in many different phases. Here's one color or one wavelength of frequency, but it's incoherent. None of the waves are lined up. And here is a single color, all in phase. So this is a laser. Laser is light amplification by stimulated emission of radiation. Okay, so it's a device that produces a beam of coherent light. So it creates a beam like this. It's not a source of energy, but if you put energy in, you can get coherent light out. Okay, the symbol F in the equation E equals hf stands for the frequency of energy. No, Planck's constant, no, that's h. Energy is E. A photon with energy E. So that's what the frequency the symbol F in the equation E equals hf stands for the frequency of a photon with energy E. That sounds right. Which of these colors of light has the most energy per photon? Well, white doesn't have a photon. It's it's all the colors of the rainbow. It doesn't depend on brightness. Blue is shorter wavelength, high energy, so it's red is the answer. Most energy per photon, of course, is blue. Red has lower energy per photon. Electrons making transitions between the energy states of neighboring atoms occurs mainly in hot solids. That sounds okay. Lasers, that's something else creating coherent light. Phosphorescent materials, that's within the energy levels of an atom. Light emitting diodes, that's a totally different process involving semiconductors. I think hot solids is the best answer. When an atom is excited, one or more of its electrons has been given to excess vibration. I'm not sure what that means. Boosted, that sounds good. Boosted to a higher energy level. Displaced, probably not. Ionized, that's if an atom lost an electron. So that's not right, so it's boosted. Discrete spectral lines are clearly evident when excitation occurs in a solid liquid gas. So gas is the best for this. The property of F proportional to T, frequency proportional to temperature, tells us that the frequency of light is proportional to its temperature. That doesn't really make any sense. A light source is proportional to its light's temperature. Frequency of a light source is proportional to the light's temperature. I'm not sure what we mean by light's temperature here. Frequency of light emitted by a source is proportional to the temperature of the source. That sounds really good. Frequency of friction and temperature are related. This is the third one is the best. So the source's frequency of light emitted, the peak, is proportional to the temperature of that source. The peak of brightness frequency radiation, the peak of a brightness frequency radiation curve shifts to the right for as the temperature goes up, the frequency goes up. So it's going to be high temperature emitter. Using a spectroscope to examine light from an incandescent lamp reveals, it's a continuous spectrum. Distinct spectral lines, no. Different colored spectral lines, no. It's going to be continuous. Each of the spectral lines seen in the eyepiece of a spectroscope is due to differences in temperature between various atomic energy levels. I don't think temperature has anything to do with it. Photons cascading between energy levels in atoms. That sounds good. Electrons making transitions from one energy level to another. That sounds even better. Transitions, not cascading, not necessarily. Transitions is the better word. The combination of light frequencies emitted by excitation. So that's even better, because transitions could, it says spectral lines. So spectral lines could be, this is emission, and so we're seeing, it could be absorption. So I don't think we want to go with emission. I think we want to go with transition. The transitions from one energy level, if it's an excitation, that would be an absorption spectrum. If it's de-excitation, that would be an emission spectrum. So I'm going to go with the third one. Yeah, okay. To determine the identity of elements in a star, we investigate the stars: emission spectrum, absorption spectrum, continuous spectra, emission spectra, absorption spectra, continuous spectra, Doppler shifts. So, because we're looking for the identity of elements, we're looking for that fingerprint. And because light from a star goes through the star's atmosphere, we're looking for an absorption spectra. Okay. When blue light falls upon a material and causes it to fluoresce, the fluorescent color can be, red sounds possible. Violet and ultraviolet are higher energy than blue light, so those are not possible, so it's got to be red. Light from an incandescent lamp is composed of a jumble of frequencies. That sounds good, because it's continuous. A series of well-defined spectral lines, it's continuous, so no. Blank spaces in an otherwise continuous spectrum, no, we don't see that. We just have continuous. Mainly ultraviolet photons. Holy, that's a bad incandescent lamp. So I say a jumble of frequencies. The spectrum of light emitted by an incandescent source is, we just said that's continuous. The dark lines in the solar spectrum represent light that is absorbed, emitted. It's dark lines, so that's not emitted. Absorbed by the sun's atmosphere, that sounds good. Absorbed by atoms on the sun's surface, that also sounds good. But I suspect the atmosphere is the primary absorber. Cancelled by destructive interference, that's not right. So it's got to be the second one. Okay. Light from a fluorescent lamp is due to, we're going to do incandescence is different. Monochromatic light is a laser. Electron resistance is not really related, so excitation. Phosphorescence differs from fluorescence in excitation and de-excitation. Well, phosphorescence is like glowing, and that's because the de-excitation of electrons is happening with a time delay, and fluorescence is same de-excitation but immediately. So there's no difference in energy levels, amplitudes, or discreteness. It's really those time delays that's the primary difference. All the light in a laser beam has the same laser, so the same frequency, the same phase, has the same speeds, all of them, because it's coherent light. And that's it. So I'll see you guys next time.